This is a presentation on behalf of Work Package 4 for the final meeting for patrols. My name is Vicky Stone and I'm going to give you an overview of some of the more recent achievements in the project. So you already know that we've generated 2 liver models and 2 gastrointestinal tract models, which have been presented at previous meetings. So the liver models include one for primary human liver tissues with up to 4 cell types, with a range of different phenotypes ranging from healthy to fibrosis. And this model shows that if you have an increased disease status, then this enhances the response of that microtissue to the nanomaterials. This model has also been shown to identify a novel endpoint such as connexin 32, and it allows repeated exposure to the nanomaterials for up to 21 days. The microtissue based on the HepG2 cell line from Swansea will be described in a few more slides from Sam. For the gastrointestinal tract model, we have again 2 models, one from IUF, which will be described in a few moments by Angela in more detail, and one from Heriot-Watt University with Victor Udo, which uses the CACO2 cells combined with HT29 MTXE12 cells, which make mucus, and Raji B cells, which are a lymphocyte. These can be cultured to make an M cell model. So this is a phenotype where the CACO2 cells flatten down and lose their microvilli and start to behave like the cells in a Peyer's patch or the immune tissue of the gastrointestinal tract. They can be used for a range of different endpoints, and they've been used in collaboration with Gracious to allow assessment of different nanoforms of silica to work out how similar those different nanoforms are from each other and whether they can be grouped. In addition to the development of 4 different models, MISFIC have also conducted some high throughput screening and developed methodology for this in vitro using again 3D HepG2 cells, but this time including a reporter of green fluorescent protein that allows these cells to respond to various stresses. When combined with confocal microscopy, this has proved to be a powerful tool to understand mechanistic responses to nanomaterials, including the role of oxidative stress, DNA damage signaling, and various stress indicators. For this presentation, we're going to focus on one deliverable in particular, and that's deliverable 4.6, which has looked at the ability to transfer the different SOPs between the different laboratories within the work package. So at the start of this task, we decided to share 3 different models, one gastrointestinal tract model from IUF, the liver spheroid model from Swansea, and the InSphero model from of the liver as well. We looked at different endpoints for each model, different treatments, not always nanomaterial treatments, sometimes a drug treatment, and we decided upon the dosing regimen as well.
My name is Samantha Llewellyn, and today I will give you an insight into the development of an advanced in vitro 3D liver model for nanomaterial testing. Based on 2 principles, one being that the primary human cell types can exhibit high interdonor variability, and the second being that standard 2D cell cultures don't encapsulate the intricate multicellular interactions and metabolic activity observed in vivo as well as the 3D structures, we began to develop a 3D cell line based liver model. So the aim of this work was to advance an existing 3D in vitro liver model and enhance the physiological relevance, improve the capability with toxicity endpoint tests, and develop a 3D model able to remain viable for 14 days in culture. So this was to allow for both acute, prolonged, and repeated nanomaterial exposure regimes to be evaluated. Once this HepG2 Spheroid model was optimized, we fully characterized the model over a 14-day culture period and published the method in Jove Journal last year. This 3D liver spheroid model has been shown to remain over 70% viable for 10 days in culture, 14 days if you include seeding time, and retain its liver-like functionality through the increased production of albumin and urea until day 14, where it begins to tail off in parallel to the drop in cell viability. This model is easily accessible, simple to construct, and quite adaptable, allowing us to add other features, which I'll come back to later on. Following the nanomaterial exposure period, the supernatant and spheroids can be harvested simultaneously or independently if necessary. As a result, this 3D model is compatible with a number of biochemical endpoints, from cytotoxicity and liver functionality to inflammatory markers, gene expression, and even DNA damage. One key feature of this proliferating 3D in vitro liver model is its ability to support fixed DNA damage assessment via the micronucleus assay. With further advancement of these models to improve their predictivity, they could provide suitable alternatives to animal-based testing methods for high-throughput toxicological screening of nanomaterials. To assess the transferability and reproducibility of the model, an interlaboratory trial was recently undertaken with the HepG2 liver model. We found that the model was easily transferable with only a few minor teething issues which were easily resolved with further detail clarified in the SOP. In this part of the interlab trial, the model was transferred from the host lab, Lab 1, to an industrial CRO, Bioreliance Lab 2, for genotoxicity assessment. Both labs assessed acute 24-hour exposure to a positive control chemical, benzoapyrene, across a similar dose range from 0 to 8 micromolar, as shown here in Table 1. For genotoxicity, the lowest observed adverse effect level, at which the first significant induction of micronuclei was observed, was almost identical between the two labs, with a similar fold change in micronuclei seen. For the interlab trial done within Patrols itself, a longer-term 5-day exposure to barium sulfate nanomaterials was tested in both the host lab, Swansea, Lab 1, and the transfer lab, Heriot-Watt University, Lab 2. The IL-8 pro-inflammatory response was assessed comparatively in this trial, following prolonged exposure to 0.2 and 2 micrograms per ml of barium sulfate. As seen in this figure here, there was good concordance in the negative untreated control, with no significant difference between the IL-8 response observed in the HepG2 spheroids from Heriot-Watt Uni and Swansea Uni following 5-day exposure to barium sulfate. Both of these trials demonstrate the successful transfer of the protocol across laboratories with excellent reproducibility in hazard endpoints. This final slide just highlights the development process undertaken for enhancing the physiological relevance of the 3D liver models from the baseline HepG2 model described in the previous slides to where we finished the Patrols project. Initial progression involved enhancing the model itself to include the addition of secondary cell types. In this case, it was the addition of liver-resident macrophages, known as Kupffer cells, as these are the main cells required for initiating an immune response to help clear the foreign material. To replicate human physiology, for every 4 HepG2 hepatocytes, we added 1 Kupffer cell. This ratio worked really well as we saw great integration of the 2 cell types within the spheroid, as shown here in this confocal microscopy image. Next, we looked to adapt the environmental conditions by replicating the oxygen concentrations available in the liver within the human body. Atmospheric oxygen is normally at 21%, which is between 10 to 18% higher than that found in the liver. In the human liver, oxygen concentrations range from 3 to 11%, so in order to represent this, we used a sealed hypoxic incubator to grow the cells at physiological oxygen concentrations, in this case 5% O2. So once established, the models were then exposed to multiple nanomaterials and specific biochemical endpoints analysed to assess the nanomaterial hazards. Firstly, we looked at prolonging the E&M exposure to replicate that of natural human exposure. Then we went on to break the exposure down into smaller repeated doses, as that again was a more realistic way in which humans are exposed to nanomaterials, for small doses repeatedly over extended periods of time. It was also considered that the nanomaterials reaching the liver may have undergone biotransformation from contact with various biological fluids whilst translocating through the body prior to reaching the target organ. So this biotransformation can transform the properties of these materials, and so a tiered testing strategy and SOP for mimicking nanomaterial biotransformation in the liver were developed. So to conclude, within this project, we have developed an advanced 3D in vitro HepG2 liver model that is able to support a range of toxicological endpoints for E&M screening. This model has proven to be successfully transferable amongst both academic and industrial laboratories alike. And then finally, additional SOPs which provide a more physiologically relevant 3D HepG2 liver model and E&M dosing regimes have been developed as a step closer to finding suitable animal testing replacements.
Hello and good afternoon to all. My name is Angela Kempfer and I'm a postdoc researcher at the Institute for Environmental Medicine in Düsseldorf. On the next slides, I will summarize the outcomes of the interlaboratory transfer conducted in patrols, here specifically the results for the intestinal macrophage model, which has been set up by 2 partner labs and evaluated for its responses to diclofenac. To briefly summarize the background of this study, the plan was to establish the IOF-developed macrophage model in stable state in 2 other patrols partner labs, which was Swansea University in the UK and AMI in Switzerland. This slide summarizes the very basics of the model. The model combines 3 cell lines, CARCO2 and the E12 clone of the HT29MTX cell line, which was seeded in a 9:1 ratio on transwell inserts and differentiated for 21 days. PMA differentiated THP1 cells were then added to the basolateral side of the transwell setup to initiate the triple culture. These cultures were maintained for 24 hours before the exposure experiments using diclofenac were started and maintained for another 24 hours. All partners conducted the experiments with stable triple cultures and with transwell cultures of the epithelial cell lines alone. The partner labs received the patrol's SOP on the stable triple culture setup, which contains information on the cell culture, the characterization endpoints, as well as quality criteria. There was some additional information sent around on the diclofenac exposure, for instance on how to prepare the stocks, as well as a video SOP on transwell handling, PMA differentiation, and the triple culture establishment. The data collection and sample analysis took place in the respective labs, and the data analysis in the end was performed at IUF. Based on the results previously generated at IUF, we of course had some expectations towards the outcomes of the partner labs. I will not go through these expectations in detail here, but use them on the next slides to compare the results and estimate how successful the transfer to the partner labs was. I will then use green check marks or red crosses to indicate whether the results matched the expectations or not. I will start with 2 endpoints that help us characterize the quality of the cultures. First, we compared the barrier formation of the epithelial transwell cultures, shown in the top graph. Even though there is some variation between the labs, we see that the TEER values at day 21 are pretty identical. More importantly, all labs obtained epithelial barriers with a barrier integrity above the critical value of 250 ohm per square centimeter. The second model characterization endpoint was the barrier integrity over 48-hour triple culture with THP1 cells, which is summarized in the bottom graph. The results of Lab 1, which is the host lab, show a very consistent TEER value range, whereas both Lab 2 and 3 reported quite some variations. Especially Lab 3 struggled with a substantial reduction in barrier integrity, which surprisingly recovered again at the end of the experiment. Next up were then the exposure experiments. As diclofenac is a strong enterotoxic compound, we focused on cytotoxicity endpoints with barrier integrity, here in the top graphs, and LDH release in the bottom. The start of diclofenac exposure is indicated by the dotted lines in graphs A and B. All 3 labs reported a strong reduction in barrier integrity after 24-hour exposure in both the epithelial co-cultures, shown in graph A, and the stable triple cultures in graph B. There was, however, a difference in the onset of this reduction, which Lab 1 already observed after 4 hours of exposure, in contrast to the other 2 labs. Also, the tendencies for LDH release were comparable between the labs. All detected an at least 2-fold increase in LDH release for apical supernatants, and low to no increase in basolateral supernatants. Only the basolateral results for Lab 3 are strikingly different, but due to the very large standard deviation, this is likely related to an operator error. The quantification of interleukin-8 release was included as a bit of a last-minute endpoint that can give us an indication for both the THP1 differentiation as well as the response to diclofenac. The graphs summarize the results of the individual labs, with the epithelial co-cultures on the left and the stable triple cultures on the right. Apical and basolateral supernatants were analyzed separately. In Lab 1, at the top, we did not detect significant quantities of interleukin-8 in apical or basolateral supernatants of the epithelial co-cultures, and no response to diclofenac. In contrast, the stable triple cultures were always characterized by increased quantities of interleukin-8 in basolateral supernatants, and a strong increase in interleukin 8 in apical supernatants after the exposure to diclofenac. For the stable triple cultures, the results of lab 2 and 3 were entirely different, as can be seen in the graphs at the bottom. Neither did they observe an increased background interleukin 8 release, nor did they detect an increase in response to diclofenac. These strong differences in interleukin 8 response were very surprising, as the PMA differentiation apparently was working very well in all labs. To sum this up, having only matched 50% of the expectations of the host lab, one might think that this study was not very successful. But keeping in mind how difficult the coordination of this task was, that there was no hands-on training possible and no previous experience in handling complex models, it's really not a bad outcome. What we have confirmed, and that is surely not only true for the intestinal model, is that such an interlab transfer requires very detailed instructions, especially if hands-on demonstrations are not possible. For the data analysis in particular, well-defined quality criteria are very important, as they make the data analysis later on much easier. In retrospect, it would have been helpful to first focus on setting up and characterizing the model against some benchmark endpoints before jumping right into the exposure experiments. One of the non-matching outcomes, that is the barrier integrity during the triple culture, is likely related to a lack of experience of the operator and the fact that even the earliest outcomes had to be included in the analysis. The other two endpoints that did not match the IOF data were related to the THP1 cells, which might really be the bottleneck of this model. If we only focus on the epithelial co-cultures, the results between the labs are a lot more homogeneous. This is an inconvenience in this particular case or in this particular study, because even though the trends are the same between the labs, we have quite some variations between them. But more importantly, these differences might be of much more relevance when establishing the inflamed state of the model, as that really depends on the PMA differentiation quality of the cells, as well as the inducible cytokine response of the THP1 cells. So altogether, the outcomes are quite promising and give me the confidence that both the model in itself, as well as the instructions that we have developed for it, are of sufficient quality to transfer the model to another lab. The training and routine in handling the cell lines and the model then, of course, have to be established independently.
I'm just going to finish off with a description of the interlaboratory comparison for the primary tissue liver microtissues. The microtissues from Spheroid were shared with Swansea University, Heriot-Watt University and NRCWE. These microtissues were treated with titanium dioxide or zinc oxide particles or with Triton as a positive control. And then adenylate kinase was used as an indicator of cytotoxicity. There was really good comparability between the cytotoxicity data generated for the three laboratories using this tissue. In addition, the IL-8 production was also assessed for two of these laboratories, and again, these were quite similar to each other for the treatments and the endpoints and the time points measured. One of the useful things that came out of the interlaboratory comparison was the ability to improve the SOPs, and I'm just going to give you one example for this here. So on the left-hand side, we have a HepG2 liver microtissue generated by one of the labs receiving the SOP from Swansea University. You can see that these cells did not form spherical microtissues in these experiments. But after some discussions with Swansea University, they provided some tips, and the host university or the receiving university was able to improve their protocol so that they could now get quite nice spherical microtissues. And this led to some additional information being added into the SOP in order to provide the clarification for this. Some final conclusions from the interlaboratory studies were that the three models could be transferred between labs with at least two naive labs receiving those models. Most of the endpoints showed some similar trends, although there were some variations in the data. And the SOPs were modified in some cases following feedback from the naive or recipient labs. So I'd just like to finish by thanking all of the Work Package 4 partners. They've done an amazing job during the last 3 to 4 years, have worked really hard, and it's been an enjoyable group of people to work with, and you've made my job very easy. So thank you very much.